Hello, my dear children of class 11 science. Today we do again continue with the chapter that we are doing, that is called kinetic theory of gases. Okay, so this is a chapter, only one chapter, and it comes under the unit, that is unit number 9. So we are in the second last unit of class 11 syllabus. Now in today's class we derive the expression of the pressure of an ideal gas. So now this is the most important part of kinetic theory of gases, because children, you in the last class you learned about the kinetic theory of gases, the assumption for the kinetic theory of gases. Okay, now from the kinetic theory of gas, we basically we need to measure the pressure exerted on by the what gas? Ideal gas. So children, now whatever expression we derive is for ideal gas, and you know what is ideal gas? Ideal gas is also called a perfect gas, which follow Boyle's law, Charles' law of pressure, and even the gas equation for all condition of temperature and what? Pressure. Okay. Now in order to derive the expression, so we basically take an ideal gas. So we take an ideal gas, okay, and this ideal gas we take in a vessel, and we take what vessel? A cubical vessel. So you can see that a diagram. This is a what vessel? Cubical vessel. Cubical what? Vessel. That means a vessel consists having all the sides, length, breadth and height all same. Okay, so this is the cubical vessel. But this vessel we take in such a way so that this wall, these are the wall of the cubical vessel, okay, are perfectly elastic. Now when the wall of the vessel are perfectly elastic, then definitely the momentum and the kinetic energy remain conserved, so that when the molecules collide with the wall of the vessel, okay, so there is an equal amount of momentum that is transferred by the molecules to the wall, because you know when the collision takes place with the wall, the molecules will return back, okay, without any loss of energy, and even the momentum will be conserved and all. That is, momentum conserved means what happens? Whatever momentum, the momentum will change, okay, when molecule collide with the wall, then equal momentum will be transferred by the molecules to the wall, so that the elastic collision which takes place under this wall is also called what elastic? Perfectly elastic collision. Now as you know children, that I have taken what vessel? Cubical vessel. All sides are equal, so I consider each side of this cubical vessel is what? L. So L, small l, is the length of each side of the what vessel? Cubical what? Vessel. But this vessel must be perfectly elastic. Side of cubical vessel, which is what? Let me just add, continue, which is perfectly elastic. So this is also one important condition, perfectly what? Elastic. Now there are the gases. Okay, there is a gas, ideal gas, and this gas has molecules. Now there are so many molecules present in the ideal gas, okay, but every molecule has a what? Mass. So what I do, I write down, let small m, I'm writing the symbol small m, be the what? Mass, the mass of what? Each molecule, the mass of what? Each molecule, okay, of an what gas? Ideal gas. So it can be any ideal gas, it can be oxygen, nitrogen, hydrogen, any ideal gas, okay, but every molecule has a mass, that is what? M. But you don't know how many molecules are there. There will not only one molecule present, there are an n number of molecules present. So I write down, let small letter n, so I am writing the symbol small letter n be the total number of molecules, total number of molecules, okay, total number of what? Molecules in the gas. Now this vessel which has place where the gas molecules are consist of, okay, in such a manner so that you can see this vessel, three sides is expressed by three coordinate axes. So this side of the vessel is expressed by z axis, this side is expressed by y axis, and this side is taken by x axis. That means the vessel is placed in such a manner so that there are three edges, these are the three edges, okay, and which represent three sides are represented by the coordinate axes. So we represent this side by the x-axis, we represent this side by the y-axis, and we represent this side by the what? X-axis. Now why we need to represent this manner? Because the motion of molecules inside the vessel is usually a what motion? A three-dimensional motion. That means when a molecules acquire a velocity, the velocity acquired by every molecules can be represented in 3 coordinate axes. That means it can be, the velocity can be split into 3 component: x component, y component and z component. Okay, so I consider that suppose any one of the molecules is moving in this direction with a velocity b. Suppose one of the molecules in a vessel acquiring a velocity what? B. Okay, at this point. So I write down, let b be the what? Velocity. Let be the velocity of what? A molecule. Any one molecule. And you know, one of the important assumptions we have done in the last class is that all the molecules are identical with respect. That means if one molecule has one mass m, another molecule also has mass what? M. That means all the molecules present in this ideal gas molecules present in the ideal gas are identical with all respect. Okay, so we are taking any one molecules. Okay, any one molecules of the ideal gas which is moving with a velocity, say what? B. So at any position when the molecules move with a velocity b, remember this part children, this velocity has to be split into 3 components, because this motion is a 3-dimensional motion. So 3 component means the velocity, this velocity can be expressed along x-axis, along y-axis and z-axis. So for that I write down, let bx, by and bz. Okay, these are the component of velocity. I write down components of what? Which velocity? Component of velocity b. Okay, along x, y and what? Z axis. So that's why this motion must be considered as a 3-dimensional motion. And when we measure the pressure, okay, then we take with one molecules, okay, whose velocity can be represented along x, y and z axis, so that other molecules also acquire the velocity in the similar manner. Now this velocity b, which is the magnitude of velocity b, or magnitude of velocity, okay, can be written in terms of the magnitude of the component velocity, which is nothing but bx, by and what? Bz. And in case of 3 dimension, the magnitude of velocity b, any velocity or vector quantity, okay, can be written by b square equals to bx square plus by square plus bz square. So children, this relation which I have written out here is actually based on writing the magnitude of any vector quantity in 3 coordinate axes. And this part I have already taught in one of the chapter or topic called vectors. Okay, in one of the chapter called motion in a plane. At that time I taught about the vector. Okay, 2-dimensional vector. The vector can be represented in 3 component. Okay, so these are the relation which need to understand. So b square, the magnitude of vector velocity, which is a vector quantity, is given by b square equals to bx square plus by square plus bz square. So let me just consider this by equation number 1. Now, as I said, motion of the molecules of gas is a 3-dimensional motion, and 3-dimensional motion is usually more complex than a 1-dimensional motion and 2-dimensional motion. Okay, so under this case, what we do, we have already considered one of the molecules of the gas, okay, which is moving with the velocity b. But this velocity we have split into 3 components. Okay, now what I do, now we consider that the motion of these molecules along what axis? X-axis. Along what axis? X-axis, and is moving with how much velocity? Bx. Okay, definitely these molecules will collide with the wall of the container. So if this velocity can be split in 3 components, means I write on this way. B can be written in this axis as bx, b can be written in this axis, can be split in this axis as by, and this b can be split into this component, and that is what? Bz. Okay, so bx, by and bz are the 3 components of velocity of b along x-axis, y-axis and z-axis. Okay, but see, we are taking these molecules in a cubical vessel, and this vessel has this surface. This is the surface of the vessel, and consider that surface is what? A. This is the one of the surface where the molecules of a gas which is moving along x-axis, okay, with the velocity bx, will collide with this surface. So when the collision takes place, definitely that molecules will what? Rebounds back or return back, but with such a way so that the momentum of the body will change. So molecules will change. So remember children this part, when one molecules collide with the wall, the momentum will change. But this momentum of this molecule change in opposite direction, because if it move in this direction means after collision this molecule will move in this direction. So definitely along this axis, that is positive x-axis, when it moves with the velocity bx, when it return back, it moves with the velocity opposite to this velocity, so that there is a change in the momentum. But under perfectly elastic collision, whatever amount of momentum that is changed when the molecule collide with the wall, equal momentum will transport by the molecules to the what? Wall. Equal momentum will transport by the molecules with the what? Wall. So children, if you look at this diagram, see, if one of the molecules is moving along what axis? Say x-axis with a velocity b, and definitely it will collide with this face of the wall. Okay, and when it collide, what type of collision takes place? Perfectly elastic collision. In that case, the molecules which already moving with a velocity bx, the positive velocity of bx, after collision will rebounds back in this direction. At that time, the velocity of the molecule changes from bx to what? Minus bx. See, colliding with the wall, just like suppose this is a wall. If the molecules collide along x-axis with a velocity bx, after collision it will return back. It rebounds back in the opposite direction. At that time, the velocity acquired by the molecules will be minus bx. So children, look at this. Velocity changes from bx to minus bx, and this is along x-axis. So with this change in velocity, what will change also? Momentum will also change. And when we measure momentum change along x-axis, is momentum changes from what? Mbx to minus mbx, because momentum is what? Mass into velocity. Okay, but initially the molecule moving with a velocity bx, having mass m, means what is the momentum of the body before it collide with this wall? Mbx, and this is the initial momentum, and it changes to minus mbx, which is the final momentum, because after collision the molecules return back this direction with a momentum, and that momentum is minus mbx. So what is the change in momentum? The change in momentum of molecules along x-axis we can write by symbol delta p equals to final momentum minus initial momentum. So your final momentum, children, is minus mbx minus initial momentum is mbx. So this is the final momentum minus initial momentum. So just see, same sign means it will be added. It will be minus 2mbx. mbx minus sign, if we add means minus 2mbx. So this is delta p. So what is the change in momentum? Minus 2mbx. But this is along x-axis. Okay. Now according to the law of conservation of momentum, see, momentum is conserved because collision is perfectly elastic. Okay, and under perfect elastic collision, the momentum is conserved. Momentum is what? Conserved. So I write down for perfectly what? Elastic collision. For perfectly elastic collision. Okay. From the what? From the law of conservation, law of conservation. Okay, law of conservation momentum. From the law of conservation of what? Momentum. Equal momentum, let me just tell you children this part. Equal momentum will be transferred by that molecules to the wall also. This is the momentum transferred by change in momentum of the molecules by the wall. Momentum has changed because of the molecules collide with the wall. But it's not that momentum is only changed with the molecules of the molecules when they collide with the wall, but that molecules also transfer equal momentum to the what? Wall. Okay, so I write down law of conservation momentum. Equal momentum. Okay, equal momentum is transport. Equal momentum is transport to the wall, and that momentum is given by plus 2 mbx. Now why plus 2 mbx? Because this is the change in momentum in the negative axis, means that molecules transfer momentum, equal momentum in the opposite direction to the wall, and that is plus 2 mbx. So this is the momentum which is transferred to the wall. Now after collision with this phase, the molecule will not stop moving. The molecules continue in a state of motion. So what happened? The molecules return from A, okay, which collide with the wall opposite to what? 1. That means one molecule is moving along x-axis, collide with this wall, return back, and again collide with the another wall which is opposite to this. So collision happened this way, like this one. Okay. Now it will rebound back, and again it, after colliding with this particular opposite wall of this phase, again it will go back. Okay, again it will go back and have collision with this wall again. That means the collision takes place in a repeated manner or in a successive manner. That means a molecules cover a certain distance when it have how many collision? 2 successive collision with this phase. First collision rebounds back, collide with this phase, and again goes and collide with this phase. So just look at it. After collision with this phase, it will go this side. How much distance it will cover? L. And again it will come and collide, means how much distance will cover? L. Going this side is L, again come back and collide with this is L. So L plus L is how much? 2L. So how much distance that will cover by a molecules to have 2 successive collision? This phase 2L. So as I said children earlier, that a molecules cover 2L distance between 2 successive collision with A, but moves with a velocity how much? Bx. Okay. Now in this case, definitely that molecules takes certain time to have 2 successive collision. Okay. It takes certain time to have 2 successive collision with the wall. So I write down therefore time taken by a molecules. Time taken by molecules to have 2 successive collision. To have 2 successive collision is given by time is distance by velocity, because velocity means distance by time. So distance means what? Time is distance by velocity. But for 2 successive collision, what is the total distance covered? 2L. The distance covered is 2L. And even for 2 successive collision, the molecule is moving with the velocity how much? Vx. So this is the time. Thus a molecule collide Bx by 2L times in 1 second. Now this Bx by 2L time is also the frequency, means how many times the molecules have a collision. In how many seconds? Just in 1 second. So in 1 second, how many times the molecules have collision with the wall or with that phase? Bx by 2L times. Okay. Now children, now we can easily calculate how much momentum that transferred to that wall A just in how many seconds? 1 second. Okay, so that momentum transferred to the wall A in 1 second is actually calculated as momentum transferred in 1 collision into number of collision in 1 second. That means in 1 second how many collision takes place into momentum transport just in 1 collision is calculate. That calculation, that product measure the momentum transport to the wall A in how many second? 1 second. So we know the values. The momentum transport in 1 collision, only 1 collision is plus 2 mbx. And children, remember this part, we are dealing this with the collision along x-axis. This is for x component of that velocity. The number of collision in 1 second that we have already calculated, bx by 2l. See, bx by what? 2l. Okay. So now, so what is the value now? It will be plus 2m. Bx into bx means what? Bx square by 2l. So this is the momentum transport to the wall in 1 second along which axis? X-axis. This is along which axis? X-axis. But when there is a momentum change takes place in 1 second, then the rate of change of momentum, okay, according to Newton's second law of motion, is equals to the force exerted by the molecules. The force exerted by the molecules on the wall. So when the momentum collision takes place, means force will exert by the molecules on the wall. And that force means nothing but the rate of change of what? Momentum. So children, as I have already explained, we need to apply what? Newton's circular motion. And Newton's circular motion measure how much force that is exerted by the molecules on the wall. And that is equals to the rate of change of momentum of a molecules. And this rate of change of momentum is actually nothing but what? Okay. Equals to the momentum transport to the wall A just in how many seconds? 1 second. Which means this value, okay, of force is equals to mvx square by what? L. So this is the force exerted by the molecules on the wall, but along which axis? X-axis. But children, this expression of force exerted by the molecules, we have taken only for one molecules. But children, in a gas vessel, okay, there are so many molecules are present, and we have already considered n molecules present in a gas, and all the n molecules can have a collision with the wall along which axis? X-axis. So to calculate the total force exerted on the wall A by n molecules, but along which axis? X-axis, we can calculate as mbx1 square by L, I'm writing this way, plus mbx2 square by L, plus dot dot dot, it will go mbxn square by L. Now I have taken bx1, bx2, bxn. These are nothing but the velocity of the molecules, n number of molecules along x-axis. But all the molecules are identical, their mass is same, and the collision takes place on the same phase with the same distance, so L, L, L also same. Okay, so in this expression we can take common m by L. So if I take m by L common, so inside the bracket it will be bx1 square plus bx2 square, and this will be dot 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 bxn square. Okay, as I said already, bx1, okay, is the component of velocity of molecules, first molecules. Similarly, bx2 is the component velocity of second molecules. Similarly, it will go on, and bxn is the component of velocity of n molecules. Okay, so this is the force, total force exerted on the wall A by n number of molecules along which axis? X-axis. Now in order to now derive the expression of pressure, now we calculate the pressure. Okay, we do continue in the next YouTube video. Okay, in the next YouTube video we do with the same expression, the same condition, but we measure the what? Pressure.